In this video, we're going to review how to write and model chemical equations. We'll start off by reviewing how to count atoms when we see a chemical formula, how to model just that chemical formula, and if we see a model, how do we read it to interpret the chemical formula. And then we'll look at an equation and determine if it's balanced, because as you remember, we need to make sure the law of conservation of matter is followed, which means in our case, we'll make sure we have the same number of atoms of each element before and after, or on the reactant side and the product side of the chemical reaction. First example, use the coefficient and subscript to model the molecule and atoms below. As you probably remember, our coefficient is the large number in front. So over here we have a 3. And the subscript is going to be the small number that comes after the element or the symbol. The model for H3 is 3 H's all bonded together. As you can see, they're the same color because they are all 3 of the same atom. The model for 3H, however, is 3 separate hydrogen atoms. In this case, they are not chemically bonded, and in this case, they are bonded. Okay. How are they similar and different? So H3 is different because the atoms are chemically bonded, and we have a molecule because of that bond. 3H, we do not have them bonded, and this is a pure element. We just have them by themselves. They are similar because in both situations we have 3 hydrogen atoms. Example 2, use the models below to write the chemical formula. So we'll write it at the very end. Our first model, I see a 1C, which is carbon, and I see 2 oxygens. In our second model, I see something similar, but I see more of it. So in similarities, they both have 2 oxygen atoms and 1 carbon atom chemically bonded together. And both of them, they're both pure substances. In this case, pure carbon dioxide, CO2. The first one is different because it only has 1 molecule, and the second one is different because it has 4 molecules. So if there's only 1 molecule, there's going to be no coefficient. So in this case, we have C for carbon, and we just have 1, so there's no subscript. And I have 2 O's, 2 oxygens, so I will write O2. The second model is made up of the same molecule, 1 C and 2 O's, CO2. However, the coefficient will tell us how many molecules we have. 1, 2, 3, 4. And there we have it. CO2 versus 4 CO2. What if there's parentheses in the chemical formula? How do we model that? Well, I see that I have Ca, that's calcium, in case you didn't know. That's a single atom of that element. So we have Ca. The OH in parentheses just means that the O and the H, the oxygen and the hydrogen, stay together when they're bonded. So we have 1 OH group, you might say, or 1 OH pair. And the subscript means that there's 2 OH groups. So here's my other one. So as you can see, there's 1 calcium. There are 2 oxygens, and there are 2 hydrogens in this chemical formula for a total of 5 atoms. Lastly, let's take a look at a chemical reaction. This one shows the reaction for rust. We will draw a model and determine if it is balanced. So the chemical equation they gave us is 4Fe. So I must have 4 single iron atoms, and as you can see in the key, the Fe is the gray circle. So I have 1, 2, 3, 4. They are not chemically bonded. 3O2, so I have my O2 molecule, and then I have to have 3 of them. So you can see 1, 2, 3 of them. Okay, but there's a total of 6 oxygens there. Let's write that down just in case. 6 oxygens. Here I have 4 irons. And let's see, on the product side, I have 2 molecules of Fe2O3. So here's the first molecule. I see my 2 irons in gray and my 3 oxygens in white. And then my second molecule is indicated by the coefficient 2. In total, I have 4 Fe, 4 gray, or 4 iron, and 1, 2, 3, 4, 5, 6 oxygen. So, taking a look, it appears that this chemical reaction is balanced. And there we go.